Let's now talk about regression. So when we are talking about regression, we are talking about predicting a real value. So let's assume that we have a function f of x. So the target R is in fact f of x plus some noise formalized as epsilon here. So we have this epsilon, which is the noise, and then we have the dependent variables and the independent variable that is x. So we want to approximate f of x using some hypothesis, which is h of x given theta. So we are using about the same kind of approach that we had so far with classification, but in terms of regression. So we still have a function h with some parameters, and we try to estimate the values of these parameters that are fitting well the predictions. But now the predictions are not classes, they are real values. So we can assume that at first the noise is a Gaussian white noise centered at 0. So that means that we have a 0 mean with a constant variance sigma square that is describing the noise that we have in our function. This is an assumption, but it is relatively reliable. So in such case, we can say that the somehow density, the prediction we are making based on x for R follow a normal distribution that is centered on the h function that we are looking for with a sigma that is corresponding to the level of noise. This gets us to some approximation of our function for regressing it. So let's assume that we have a data set here. The data set is made of xt and rt. So remember that rt here are real values. So we have this pair of two scalars, xt is a scalar, rt is a scalar. We are still working in one dimension. We will work with the multi-dimensional case next week. So we say that we are looking at the log likelihood of this with a given data set, assuming that the data here are ID, so they are identically distributed and independent. So let's use the likelihood here, Px and R, which is basically the union of getting x and R at the same time. We can develop this as the probability, the likelihood of getting R given x times the likelihood of getting x. So we have two likelihoods that we are multiplying together to get the P of x and R. From that, we are evaluating the log likelihood for the data set. So we say, what is the log likelihood of having such parameterization over that data set? So we are using the log and the product of the pxtrt. So we are making the product of all xtrt, the pxtrt from our data set. So with this multiplication, we apply a log. We are first converting the pxtrt as what we have here. So we are converting this into that. So this is the same thing. We have this component, which is the first element, and that component, which is the second one, which is the expansion of pxtrt into prt given x, px. As pxt is independent of theta, we don't care more about this here because it has nothing to do with the parameterization. We know also that prt given x is following a normal distribution. We just showed that the slide before. So we say that prt given x, the likelihood of R given x, is a normal distribution with a mean corresponding to the h and with a standard deviation corresponding to the noise level. And so here we have something like this. We are expanding this with the log of the product of, this is the usual Gaussian distribution equation, where we replace the mu with the h, xt, theta. So this is, I would say, what we put as the mean. And we have the RT here, which is in fact the value we are looking at, given that we are looking at likelihood of R given x. So if we expand this, we get something like that. So we are applying the log on that. And so we are able to get this thing here. We have the log of this thing times that thing here. And expanding it further, we got something like, given it is power of n, so this thing is converted to that. So this is getting here. So all this is getting to minus n log square root of 2 pi sigma correspond to that element. And this thing here is what is in the brackets there. So now we will look at doing something with the least squares estimate. So this is another path to do something really similar. We will use then an error function. So this is not the expectation, this is the error. So let's look at the error function we call the least square error. So basically it's the error of our estimate theta over the data set. So basically we are looking at the difference between the label, somehow the target value versus the prediction we are making. So we are looking at the difference between these two, RT minus H squared. So this is really what you call squared error. So this is super common criteria, and we are doing the sum of this over all samples multiplied by 1/2. So why using 1/2 here? It's a matter of simplifying the developments later on. And so we have the maximum likelihood, which is what we have before. Given that n log the square root 2 pi sigma, this thing, and 1 over sigma square are both independent of theta, we don't care, the theta is not there, these are constant. We can simplify the likelihood function here, given that we are looking basically at the theta as this thing, which is quite the same than that thing up to the minus sign. The point is that we are minimizing the error, we are maximizing the likelihood. So these are basically the same equation, except that we are having a sign and we are minimizing one while maximizing the other. So minimizing the squared error is giving us a good estimate that is totally coherent with the maximum likelihood estimate. So that's a solution. So that's the approach. That's a good approach. I would say that's one that we are presenting here. That's not the only one, but that's a good one that we can use to estimate the parameters theta. So now let's define a more specific case. So we add this function h. We haven't described it before, but if we are expanding it, we get something like this. We get function h that is equal to wxt w0. This is a linear model, a super simple function, something that you saw at high school, like function ax plus b. This is the usual form in one dimension for a linear model. So we are using the same model, except that we have w1, w0 instead of a and b as parameters of our model. But these are the parameters. W1 and w0 here are in fact the theta of our model. So with this linear model, we can then develop the equations to estimate the parameters according to the least square error criterion. So now we are looking at the least square criterion error. So we say, okay, let's compute the derivatives, the derivative of the function for w0, making this equal to 0. So the derivative here is directly that thing. We make this equal to 0. And so we are isolating then summation of RT equal to this thing here. So we are getting w0, w1 on one side. So we done this here. Then we are making the derivative again, but according to w1. So this gives us that equation here, and we just kind of simplify it. We get into that equation in that form. So we have two equations, and we have two unknowns, w0, w1. So, but what we can see here is that there are some kind of patterns. These forms are relatively regular. And so we can reformulate this into a matrix formulation this matrix formulation makes things much simpler in terms of implementation, given that computers are really good to manipulate matrices. And so, and also in terms of developments, it makes things, I would say, easier to manage in terms of developing the equations and getting some regularities from it. So basically, if we get into that linear system of equations, AW, so matrix A times vector W is equal to vector Y. And we set A, W, and Y as these. This is exactly the same two equations that we had at the slide before. And then we can obtain a W because this is what we care. You know, we want to obtain the W0, W1 values from that. So we need to multiply both sides by the inverse of A. So we are inverting matrix A with that way here. So we have invert of A times Y. So Y is basically the RT and the XT. Is on the RT and the XT. And so that way we can obtain directly the parameters W1, W0 that we need to use in terms of minimizing the least square error. So then we can look at order K. So if we are looking at order K, this is an extension, I would say, of what we have in the linear case, but now we are looking with a polynomial of higher order. So this polynomial looks like this. We have, in fact, WK, and then I've just put the xt in parentheses because, you know, the t is an index, while the k is a power. So we say that we have xt power k here. And then, so with wk as the weight for that element of the polynomial. And then we have xt power 2 times w2, w1 xt, and w0. So these are the elements composing, making the polynomial of order k. And then we can get into the similar equation system. If we are developing the partial derivatives, you know, I leave that for you to make these developments on your own. But basically, we get into that that system, that matrix linear algebra system with matrix A built that way, and matrix W here with all the k plus 1 parameters, and the vector Y also here. One nice thing we can do with that is that we can decompose matrix A as the product of matrix D that is transposed. So D transpose D. So we can see that if we are using that matrix D here, and if we just do D transpose times D, we will get the exact A here that we were looking for. And so this matrix D is simpler to manage. And we can also have the Y that is described as D transpose R. So this is even simpler to implement. And now we can solve it that way. We can see that W is equal to D transpose D invert. So we are inverting D transpose D times D transpose R. This gives us the parameters W to use in our polynomial of order K. There are also other types of errors. We have the quadratic error here. So this is what we saw so far. So this is the basic one that we use for our developments. But we also have things called the relative quadratic error. So this is basically the same, but normalized according to this thing at the numerator. So we have this summation of RT minus the mean R, so R bar here. So this is one way to do this. Give us some interesting properties in terms of normalizing, getting an error that is relative. We also have the absolute error, which is different from the quadratic error. You know, with the quadratic error, higher the errors, they are counting more. You know, if we have a difference that is 2 times bigger for one sample, it will count for 4 times more than an error that is twice small for the quadratic error, because we get 2 power of 2, so it's basically 4. with the absolute error, if we have the difference that is twice as big for a given xt, according so xt versus rt, it will count only twice in terms of the absolute error. We will not give more weights to errors that are higher. Higher errors have their importance higher, simply not more.